All right, in this video, we're going to cover what the heck confidence intervals are for means. All right, so what we have to understand is what we've been doing in the past, right? In the past, we've been doing what's actually deductive reasoning, and now we're going to move more to inductive reasoning. So recall in the last unit, we talked about sampling distributions. Here, we started with knowing a population mean mu. Like, we knew it, right? It wasn't a question. We already knew what it was, and we actually already knew the population standard deviation sigma as well. And this allowed us to get a view of what all possible sample means taken from samples of size n will look like. And this is, of course, called a sampling distribution, right? So we know the center, we know the spread, we know the shape, provided all of our conditions are met. So with this model, we can see what an unlikely and a likely sample mean would look like, even without looking at a single actual sample. And that's the whole point of deductive reasoning, right? We know what the truth is, and from that assumed idea, or from that idea of what the truth is, we can get a nice picture of pretty much everything else, right? So here's an example. I'm working with marbles, right? Everybody knows what marbles are over here. So medium-sized marbles made by a toy company have a mean circumference of 40 millimeters with a standard deviation of 3 millimeters. If we were to take a sample of size 31, what would all the possible sample means look like? And that's a sampling distribution. So you start off by saying, well, I would only assume that the average of all those small sample means, x bar, right? The average of all those sample means would be 40 millimeters, right? I mean, some might be a little bigger, some might be a little smaller, but the average would be 40. And the standard deviation, well, we have this awesome formula. You take the standard deviation of the population, 3, and divide it by the square root of the sample size, 31, and that's how we get 0.469 millimeters. Now, in last unit, we learned that, why this is smaller, why a sampling distribution has a smaller standard deviation. Well, that's because we're not talking about one marble. Yeah, one marble could be a little bigger or a lot bigger, and that's using the 3, but we're talking about a sample, and a sample has a much smaller variation, especially a larger sample of 31, right? So it's not going to be as much variation. That's why the mean of a sample is only going to vary by about 0.469 millimeters. And again, we could draw this nice picture. Now, of course, the sample has to be random. The sample size needs to be under 10% of all marbles, so that we could assume independence. And we also do need to be big enough to use the normal model, because it never said anything about the population being normal. We actually have no idea. But because our sample size is 31, bigger than 30, the central limit theorem kicks in and says the sampling distribution will still be approximately normal. So we get this awesome picture, right? And what this picture shows us is what all possible sample means look like. We know most sample means are going to come in right around 40. Some might come in a little higher, some might come in a little bit lower. And then we also could see what's unlikely. Like, we know samples way up here are going to be pretty unlikely samples to happen, and then same thing down here, samples way down here are also going to be pretty unlikely. And we continue to understand this idea of confidence, right? For example, I'm 98% confident that a sample is going to be really close to 40 in the middle. Again, why am I so confident? Well, again, 98% of samples are near that, right? And when I say 98%, that means our alpha level is 2%. It means 1% of samples are going to be weirdly or unlikely high, and 1% of samples are going to be unlikely low. So I know that 98% of samples are going to be right smack dab in the middle. And then what we could do is, we could kind of figure out what our z-score is. And we talked about this in class as well. The z-score would be what z-score marks that top 1%, what z-score marks that bottom 1%, and that's where we get the 2.3263, and that again is found on your calculator using invert norm. And some statisticians might even want us to be more strict, and they would say, well, we want to start with 99% of samples that are going to be really, really close to that true mean of 40 in the middle. And again, if you're 99% confident, then that means, 1% of samples are going to be weird, whether it be 0.5% at the top or the 0.5% at the bottom. Those are your really weird samples. And again, we could find the special z-score to mark that upper and bottom 0.5%, and we could use invert norm to do that and get 2.5758. And then continuing on, some people might even be a little less confident, like let's be 95% confident. So that means, what we're talking about when we say 95% confident is that we know that 95% of samples, by the way, we haven't even looked at one sample yet, but we already know that 95% of samples are going to be really, really close to that true mean of 40. And again, that leaves 2.5 at the top, 2.5 at the bottom. They're going to be weird samples, and that's where we can get the z-score of 1.96 to mark those values, again, using invert norm. And then we could even be as low as 90% confident, which puts 5 at the top, 5 at the bottom, and then again, we could calculate the special z-star for that as well, which would be 1.6449. And we've actually kind of talked about these things, so a lot of that should already make sense. But again, now as we transition to means, This is all, the idea of what are samples going to look like, right? Well, now we want to induce. Now we want to move to inductive reasoning, and this is going backwards. Here, we have no idea what the true population parameter is. So we decide to look at a sample to gather evidence as to what the true mean could be. So instead of knowing the truth and building the model around the truth, now we don't know what the truth is. We kind of want to find it. And the only way to maybe even begin to estimate what it is to find a sample. So what is the mean circumference of large marbles? If you remember from that other problem, we're talking about small marbles. So what is the mean circumference of all large marbles that this toy company produces? Well, oops, we forgot to write it down, so we don't know. So let's try to figure it out. So let's look at a random sample of 35 large marbles. Let's record the circumference of each marble, and then, we could do the math on our own or just let a calculator do the math for us. Let's get the mean of our sample, which we did. We calculated the mean to be 58.6 millimeters, and we calculated the standard deviation of our sample to be 4.8 millimeters. Now that's an X bar. That's not a mu. This is an X bar. That's the mean of our sample, and the standard deviation is an S, not a sigma. It's an S. It's just the standard deviation of our sample. We call this our point estimate. 58.6 is just our sample mean, our point estimate, our estimate of what the true value could be. All right, now, this does not mean that the true mean circumference of all marbles is 58.6. It's only one sample. But if we think about that sampling distribution, right, according to that sampling distribution, we know that 98% of sample means will be really, really close to what the truth is. So by saying 98% confident, what we're saying is that 98% of all possible samples of size 35 will be so close to the true population mean that if we build an interval around it, then we should capture the mean within it. So the idea is that we're just assuming that since 98% of samples are really close to the truth, then our sample mean of 58.6 millimeters is also going to be pretty close to the truth. So in fact, since we know that 98% of sample means are near the true mean, if we create an interval around our sample mean, then we're pretty confident that we're going to capture the truth inside of our interval. And again, here's that idea, right? This model shows all possible sample means. We don't know what the truth is right here in the middle. We have no idea. Our sample might end up being a little bit higher, but if we wrap an interval around our sample, we should capture that truth. In fact, the only way that we would not capture the truth in our interval is if our sample was one of these really, really high samples or one of these really, really low samples. So we would have to be one of those extremely rare 2% of samples that do not contain the truth in their interval. But again, I'm an optimistic person. I'm not a pessimistic person. So I'm not going to worry about samples that are pretty unlikely to begin with. I'm going to focus on the fact that 98% of samples are so close to the truth that I'm just under the assumption that my sample is probably one of them, hence why the truth will be in my interval. All right. Now the first problem we encounter is the standard deviation, right? We understand that to build an interval, we have to go up a couple standard deviations, down a couple standard deviations to grab the truth, or to try to grab the truth. Well, we encounter a really big problem here because we don't know what the standard deviation of the population is, right? We don't know what sigma is, so we cannot possibly calculate the standard deviation of this imaginary sampling distribution, right? I mean, we already don't know what the center is. Now we don't even know what the spread is because we don't know what the standard deviation of the population is. Well, once again, like we did with proportions, we're going to have to use something called standard error. Standard error is like the twin brother of standard deviation. It's a very, very similar formula, but instead of using sigma, the population standard deviation, we have to use S, our sample standard deviation. So this does create a little bit of an issue, and basically we rename it. Instead of saying the standard deviation of the sampling distribution, we have to say it's the standard error. Think of it as the best we can do. It's going to be close enough. It's not perfect, but we're going to let it slide. We're going to have to use it. But wait, we actually encounter another really, really big problem. We did not capture this problem with proportions, and I'll explain that in a moment. But here's the issue. The normal model really isn't that great. Well, I don't mean that. I mean, we've been talking all year about the normal model being great, but here's the issue. here's why I'm saying the normal model is not great in this scenario. Because not only do we not know the population mean, which is the center, we don't even know the population standard deviation, which is the spread. So this sampling distribution that I want to kind of think about so I can imagine where that truth may fall, I pretty much can't make it because I don't know enough information. I don't know the center and I don't even know the standard deviation. So the problem is really we are just using the standard deviation S as an estimate for sigma, and that's just really not going to be good enough. This really affects the spread of our model, so it's actually not going to be normal enough. Now, let's make sure we really understand this, right? So basically, last unit we had deductive reasoning. Here we know the population parameter, and we're building the sampling distribution. So when we work with proportions, we said, hey, we're going to use a normal model. Why? Because we know we have 10 or more successes, 10 or more failures. We know the normal model is going to apply. That's awesome. When we were working with means, we said, well, the sampling distribution is going to be normal as long as one of two things. Either the population is already normal, or if the population is unknown, then we do need the central limit theorem. And remember, the central limit theorem said, hey, if the population is unknown, as long as your sample size is big enough, 30 or larger, then your sampling distribution will be approximately normal. But that was because we knew the truth. We knew the true mean in the middle, and we knew the true standard deviation sigma. Now we're moving to inductive reasoning, and this is where we're trying to estimate the population parameter using an interval. Now, we already covered proportions. We don't know the population proportion, but that was okay, because as long as we had 10 successes and 10 failures within our sample, the normal model was still going to be pretty good. So we weren't worried about that. But here's where we encounter this issue. When we're working with means, we don't know the population mean or standard deviation. And we have no idea what the shape of the population is either. So we can't even know the shape of the model to use. The central limit theorem is not going to help us here because we just don't know the standard deviation. We don't know how spread this thing's going to be out. And the normal model is really a model that talks to us about spread, where data falls above and below the mean. And without knowing the standard deviation of the population, there's just no way that we know it's going to be normal. So this is a huge problem because we love the normal model. Everything is based on the normal model. Z-scores are based on the normal model. The probabilities we've been calculating, talking about unlikely, all that's based on the normal model. So we're in a little bit of a problem here. Well, believe it or not, but a whole new model was created by a guy named William Gossett. We'll talk more about him in class, but he built a brand new model to account for this issue of not knowing the population standard deviation. The name of his new model is the T model. Yeah, I know it's not pretty cool, it's pretty boring, but anyway, he called it the T model. And there's not one specific T model either. There's actually a ton of T models, each one based on your specific sample size. This is unlike the one and only one normal model, as long as your sample's big enough, right? Like the one in the normal model, there's only one normal model. So as long as you're big enough, the normal model is awesome. But again, in this situation, we just can't use the normal model. We have to use this new T model. But the good news is that all T models are very similar to the normal model. They're just a little flatter and more spread out. In fact, the larger your sample size, the more and more the T model will actually look like the normal model. So for small samples, the T model is really necessary, but for larger samples, really big samples, the T model and the normal model are pretty much the same thing. Now, in short, this whole issue arises since we are using the standard error instead of the standard deviation. Also, instead of using Z-scores, we now have to use T-scores that are in the T model. The good news is the formula is pretty much the exact same thing for a T-score. You take your sample mean, you subtract the true population mean, which we really don't even know, and we divide it by the standard error. And again, that's why we're using a T model. So you might see that question pop up. Why do we need a T model? It's because we don't know sigma. All we know is S, the standard deviation of our sample. That's what's causing this whole problem. Now, the shape of the T distribution is still symmetric, still mound shaped, so it does look really normal, but it is more spread out, hence why we have to kind of, deal with this issue. So here's a nice kind of picture to understand the T model. So here we have in this light blue color, right, is the normal model, the standard normal model that we all know and love. Now, all these other lines are T models. And for example, this blue line right here is for a very small sample. And notice, you're like, wait a minute, that still looks normal. I know it still looks normal. Trust me, it's just not perfectly the normal model. It's a little flatter. So imagine if I took the normal model and kind of pushed down on it. It's a little flatter. And what happens when you flatten out the normal model, you get more area out on these tails. But the good news is, as your sample size increases, the different T models look more and more. So we got this blue one, we got this red one, we got the green one, then we got this purple one. I'm really messing up my colors here. We got this purple one that you could barely even see the purple model because it is so close to the normal model for really large sample sizes. Now, to quantify this relationship between the sample size and the spread, William Gossett discovered if n is the sample size, then what he calls it as n minus 1 is the degrees of freedom of the sample. Now, I know this is going to be the one thing that kind of is like, what is he talking about? Degrees of freedom? Think of it as it's just how William Gossett categorized his many different T models. There's a different T model for every sample size. And he defined them, you would think he would have just defined them by the sample size, but instead he defined them by n minus 1, one less than the sample size. So for example, this blue line right here that I'm circling here, this must have been from a sample of size 2, a very small sample. That's why it has a degree of freedom of 1. 2 minus 1 is 1. This sample size right here in red, that would have came from a sample of size 6. That's why 6 minus 1 is 5. So I know it's kind of weird. It's just how statisticians have defined the T models based on their degrees of freedom, okay? Now, again, the degrees of freedom does seem a little bit confusing, but just think of it, this is a way that he specifically determined what T model to use based on sample size. I know it's weird, but it's a really easy formula. It's just your sample size minus 1. It's also a pretty weird name, degrees of freedom, but to me it sounds kind of cool. All right, so what does this all mean for you? Basically, it means with small sample sizes, you will need to find a special t-score in place of a special z-score. So we've talked about special z-scores. For example, 95% confident, we all know is 1.96. Well, we need to use a slightly different value. Well, thank goodness on our calculators, we have invert t, INVT. This is literally right underneath invert normal on your calculator, and invert t is going to help us get our special t-scores for t models. So to be completely honest, this doesn't really change a whole lot for you. Obviously, you do need to understand the necessity for this, but it just is using a T star instead of a Z star, a T special value. And I'm going to teach you how to find it. It's all on your calculator. All you have to do when you go to invert T is enter in the proportion at the bottom, just like we did it for invert norm, and then you also have to type in your degrees of freedom, and it says DF on the screen. So now, sorry for the typo there. So now we just have to decide how far up we need to go in order to capture the truth. That's our t-score, right? And that's what the calculator is going to do for us. So let's go back to our problem. I know we've kind of been talking for a while. Let's go back to our problem. 35 marbles. The mean of our sample is 56.8. Whoa, I really messed this up. I'm so sorry. I have 58.6 here, but down in my work, I switched to 6 and the 8, so I apologize. So let's just go with 56.8 because that's what I had in my work here. So the mean of our sample was 56.8 millimeters, and the standard deviation is 4.8 millimeters. Okay, so the 58, which I'm switching to 56.8, that's our point estimate. What we're going to do is we're going to take that point estimate, we're going to go up a little, we're going to go down a little to try to create an interval for where the truth could be. So let's find a 95% confidence interval. So very easy. Start with your sample mean, 56.8, go up and down by a t-score. This is no longer a z, this is a t-score. Now where the heck did I get 2.0322 from? Well, I went to my calculator, I did an invert t directly underneath invert norm, and I typed in 0.025, because if you're 95% confident, that'll put 2.5% at the bottom. And then for degrees of freedom, I did 34 degrees of freedom. Because remember, there are 35 marbles in my sample, so we did 34 degrees of freedom. All right, so now that we got our t-star, we're going to multiply that by our standard deviation. Oh no, I wish I could use standard deviation. In fact, I wouldn't have this whole t problem if there was a standard deviation, but I'm going to have to use what's called standard error. Standard error, remember, like I told you, is just using the standard deviation of our sample, 4.8, divided by the square root of our sample size. So same formula for standard deviation, just using our sample standard deviation instead of the population. Multiply all this and divide. Like you could type this all into your calculator at once. 2.0322 times 4.8 divided by the square root of 35. And you get our margin of error. Again, the margin of error is how much we're going to go up, how much we're going to go down, which is 1.6488. So then I just took the 56.8. I went down, I went up, and I got my confidence interval. So now I'm officially capable of saying I'm 95% confident that the population mean circumference of all large marbles is somewhere between 55.1, man, I'm really bad at typing today. That should be 55.15 and 58.49. But again, I messed that up. Man, I'm sorry for my typos. 58.45 if I round correctly. I'm not quite sure what I was looking at. I apologize. But you get the idea, right? Okay. So here's the generic formula for how to do this. You start with your sample mean. You go up and down by your margin of error, which is a t-score now, times the standard error, not standard deviation, because I'm using S. Again, the whole reason why I have to use t is because I don't know the population standard deviation. I did not have this issue with proportions. That's why we still use z with proportions. But for means, we got to use our buddy t. Now, keep in mind, to find that special t-score, you're going to use invert t on your calculator. You will need to know how confident you are and your degrees of freedom. All right, so here are the 4 steps to finding a confidence interval. Step 1, identify what it is you're trying to find. I'm trying to estimate the true population mean weight of all large marbles. Check those conditions. It's got to be a random sample. Your sample size has to be under 10% of the population to assume independence. And you still, I know that we talked about the normal model can't be used, but we still need to make sure our sample is big enough. That way we could trust the T model to work, just like we need to trust the normal model to work. So we do need to make sure our sample size is 30 or larger to be big enough. All right, here are the simple mechanics. I already showed you this formula to actually find the interval. Then all we got to do is write our nice conclusion in context. I'm 98% confident the true mean blank is between blank and blank. All right, all I want to do now is end with a final example. Run through all 4 steps. And I hope, other than this whole new T model, I hope you'll find this pretty easy. All right, Millie's been baking cookies for a few years now, and she wants to sell them on the internet. But she needs to estimate the mean weight for her cookies for shipping reasons. Like she needs to kind of anticipate how much she's going to have to pay to ship these cookies, so she needs to know how much they're going to weigh. So she selects a random sample of 36 cookies and found the weight of each cookie. The mean weight of the sample is 11.39 grams with a standard deviation of 0.82 grams. Construct a 98% confidence interval for the mean weight of all her cookies. All right, step 1 is pretty easy. I will construct an interval to estimate the mean weight of the population of all of Millie's cookies in grams. Pretty easy step. Step 2, the sample was selected randomly to avoid bias. The sample of 36 cookies is assumed to be less than 10% of all her cookies to assume independence. We don't know whether the population distribution of cookie weights is normal, but because the sample size is large enough, 36 is larger than 30, it is safe to use the t distribution. I can't emphasize enough of this, right? It's probably the 4th time I've said this, maybe even more. The reason why we have to use a t model is because we only know S, the standard deviation of our sample. That's what's causing the t problem. But hopefully you realize, hey, with invert t on my calculator, it's really not that big of a deal. All right, here's my work. I started with my formula, which had a mean of 11.392. That was my sample mean, my point estimate. I went up and I went down by my t star. Where the heck did I get 2.4377 from? Well, I went to invert t on my calculator. To be 98% confident, that puts 1% at the bottom tail, so I put in 0.01. And then I did have to put in 35 degrees of freedom because my sample size was 36. That's where I got 2.4377 from. Then I'm going to multiply by my standard error. That is using S as 0.082. Again, that's the whole T problem. I'm using S as an estimate of the standard deviation. Divide that by the square root of my sample size, 36. Once again, you could type all this into your calculator once, 2.4377 times 0.082 divided by the square root of 36. And you'll get the margin of error of 0.0333. That's all in grams, right? No more percentages. This is not percentages. These are grams. These are units. So I went up and I went down from my sample mean, from my point estimate, and I got a interval of 11.36 approximately to 11.43 approximately. So step 4, interpret. I'm 98% confident that population mean weight of all cookies is between 11.36 grams and 11.43 grams. That is a pretty small window, but again, you got to look at that as, if you're actually, if shipping comes down to a couple micrograms, then maybe that's a big interval. You know, it's all when you're working with means, it's all kind of in the eyes of the beholder here. Some people might look at that and say that's a really small interval. Others might be like, no, that's kind of larger. But you know, you don't really need to worry about that right now. We'll talk more about details in a later video. But the point is just interpreting that interval. So again, kind of confusing here, but traditionally should make a lot of sense to you based on what I've taught you guys. The key issue is understanding we need to use this new T model, which really isn't that much different than the normal model. We'll talk a lot more about it later, but hope you understand the basis of the problem, and they're actually not that hard at all.